Welcome, everyone. You are joining us for Expanding Implementation of Fast Optimization Technology for Photonics, Optics, and Quantum Manufacturing Applications. This webinar is presented by PI and hosted by us at Photonics Media. Today, you're going to hear from Scott Jordan. He is Head of Photonics for PI and a PI Fellow. As a physicist with a master's degree in finance and new ventures, he has made multiple contributions to the fields of photonics alignment automation, precision motion control, and optimization technologies. In this session, Scott is going to talk about the benefits of high-speed parallel alignment technology. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access the recording of this webinar after, and you will get links to that recording in your email. So with nothing further from me, I'd like to welcome Scott. Welcome.
Thank you very much. So let me switch over to my slides and we will begin. All right. So everybody, first, thank you very much for joining us. I am in the middle of the mountains in the Sierras, the eastern edge of California, about as far from Silicon Valley as you can get and still be in the state of California. And yet, here we are, talking on a global webinar, thanks to the miracle of photonics. And of course, I guess the message is that you can't escape photonics. Photonics is about much more than just connectivity also today. That's both the opportunity statement and, let's face it, the problem statement for the photonics industry. Let's begin. Okay, just a couple of brief words about PI. We are a global manufacturer of high precision motion equipment that spans many application fields, ranging from biotechnology to semiconductor manufacturing to industrial automation and photonics as well. We have a staff of application experts around the world. We also have specific manufacturing and centers for excellence in various places around the world. For example, our air bearing Center of Excellence is in the northeastern corner of the United States. And of course, we have a ceramics engineering operation in the historic Center for Excellence for Ceramics Engineering in Germany, and so forth. We're a global company that are dedicated to helping our customers move the needle of their respective industries. We've been in business for 52 years now. We've spanned the field from making our own piezo ceramics, which are capable of sub-nanometer motions, and all the way to large format stages and assemblies of stages. We call them engineered subsystems that you can see an example here in the lower right-hand corner, where we will do the bolting together of equipment for our customers so that they can focus on their value added. And we make everything from piezoelectric nanopositioners to these large format stages for assembly and test. Now, what brings us here today is this phenomenon we see in photonics. First, photonics it's been around for a while. It has been characterized by successively smaller connection lengths. It started to back in the 1990s, 1997 through approximately 2002. The focus was on replacing satellite links with cables running across oceans and across continents to improve the capacity to enable new applications and to reduce latencies and all of those good things. Since then, this has been the fulcrum of the data-driven age that we live in today. We have seen the continual contraction of these photonic links from transoceanic and transcontinental down to regional and metro and fiber to the home and all of these things. And then came this phenomenon of the data centers run by large companies like Google and Microsoft and Apple and Amazon. And here you have tens of thousands of servers that need to be connected together to route the information that people want for the applications that we all enjoy every day. Applications such as global webinars and, of course, uh, streaming media and social networks, all of these things. What that has meant has been a exponentiating consumption of data in the world. Even in the last year of 2020, in the beginning of the pandemic, the world's appetite for data increased by 23%. That's pretty remarkable. But the real message is, the real reason for this webinar is that it's not just about connectivity anymore. It's not just about data centers. It's about all these new applications, ranging from wearable technology to autonomous vehicles with LiDAR on a chip, quantum computing, active optical cables that allow the sort of bandwidth that today's computers and media devices are capable of producing to be sent over cables of reasonable length. The only way to do that is with photonics. And now they're even stranger new fields, such as optical computing, using photons instead of electrons to actually perform logic. So the field of photonics is expanding, and it's expanding from the space in the data center into all of these new applications. But here's the scary part. If you look at the figures, at the numbers, you'll see that even the largest players, such as Intel, in one of their slides here that I borrowed from one of their public presentations, they talk about their 2 million unit run rate for transceivers for data centers. And that's an amazing accomplishment. But look at some of these other applications that we're looking at now. Hundreds of millions, hundreds of millions, each of these applications, the wearable technology, the optical cables, the just connected cars. Clearly, photonics is not done growing, because if you add up all of those things, that's about a 3 order of magnitude jump in consumption or production or productivity of the industry. However you may want to characterize it, it's both an opportunity and a problem. 3 order of magnitude ramp. So recently in photonics, I had this editorial. It was commissioned by Epic as part of their Epic Insights series of articles and columns in Photonics Spectrum magazine. Epic is the European Photonics Industry Consortium. It's an invaluable group to be a member of. Optica is another one that is a group of industry experts and decision makers that get together and they share their issues. One of the issues that I shared with them was exactly what I just described. Last November, I was attending the Photonic Integrated Circuit Conference in Brussels, and I noticed as I was listening that all of the presentations were about these wonderful new applications and their amazing new volumes, but nobody was adding it all up. And so I ended up tearing apart my presentation and presenting something very similar to this instead, to say, we as an industry are facing an immense challenge. We need to scale. So um, the thing is about this industry, it's still early days. We are um, confronted with precisely 3 things that we need to do to keep pace. Automation. We cannot continue to do things the manual way that has gotten us to where we are. Innovation. We cannot continue using the same old tools. We just will not be able to ramp without it. Cooperation. It sounds trite, but we are all in this together. We do have an ecosystem. It's emerging, and working together, we can make the necessary ramping occur. So as the slides go on, I will describe several of these things, but as I said, these are early days. If you look at this wonderful video from the Chip History Museum, this is an Intel fab back in the early 1980s, building probably the processors that you used in your first IBM PC. And what do you notice from this? Well, the semiconductor industry used to be very labor intensive, lots of people involved, carrying product from place to place, lots of custom equipment. Today, you can build a fab from the ground up just by issuing purchase orders. That wasn't the case back then, because the big names, the tool makers that we take for granted today, that ecosystem was just being born. Now, doesn't that sound like photonics today? So, and it is. We are looking at a very similar parallel evolutionary path. Now, in terms of a Pareto analysis of where are the problems, where are the costs, where are the most important issues that we as an industry need to solve? Well, the first one from PI's perspective was to address the cost of alignment, because you need to align the photonic devices together, the chips, the fibers, the integrated optics, the lasers. All these assemblies need to be correctly positioned and with accuracies down in the region of 20 nanometers typically. That's smaller than you can get using vision, and it's smaller than you are likely to get for a generic assembly if you were to machine things to the necessary tolerances. It's just not possible to machine things to that level, with a few exceptions. So that means active alignment will be necessary for the foreseeable future. And active alignment currently, according to multiple studies, is about 80% of the cost of a photonic package. And that's because active alignment must be repeated multiple times, starting at the wafer level and continuing on through the final packaging process. Typically, a dozen, 2 dozen times, the alignment process must be performed. So obviously, if older technology means that the alignment takes a couple of minutes, that's a real problem. Just look at the wafer testing to be sure that chips on a wafer are working and that they meet the specifications before you invest in packaging the chips. So if you have thousands of chips on a wafer, and each one takes a couple of minutes to align using older technology, clearly that is a cost issue and a productivity issue as well. So this is what we went out to solve. And we did so by developing a unique technology that performs alignment of photonic devices, which today are largely multi-channel and therefore require optimization in multiple degrees of freedom. Well, the old way of doing that was to do each of these degrees of freedom independently and then repeat it over and over again until you finally reached that consensus alignment. But being able to do it in parallel using the PI fast multi-channel photonic alignment technology, FMPA we call it, it's about 100 times faster. It's not a small amount faster, it's radically faster. And this is a game changer for manufacturing and test of photonic devices. Let's consider a typical alignment problem. Looks like this. You have typically multiple peaks, multiple alignment modes or whatever, and you want to select the best one and then lock onto it. And you need to do so without making assumptions about the symmetry, the Gaussianness, and things of that sort regarding this distribution. One thing I should point out, this graphic talks in terms of optical throughput through the device. And that is typically the case for silicon photonics, but we're finding other application fields where other metrics might need to be optimized as well. So this is a generic technology, a generic problem that we're trying to solve. So the way we've done this is we've built into our controllers several algorithms that you can call at a command level, such as one, a single frequency, either rectilinear sinusoidal scan or a spiral scan. It could also be a single frequency. The single frequency means that you can choose the frequency to avoid exciting resonances in your system. It's a single smooth motion. So there's no stopping and starting to cause vibrations as well. There's the possibility you can tell the command to perform some modeling. So if it can calculate where the peak is between the scan lines, that means you can use a fairly coarse scan, which means a fairly fast scan, and still do a good job of localizing that peak. Now, what I showed you was the slow motion view. The actual time it takes to do that is about 300 milliseconds. So again, fast. It's all about speed. The second algorithm that we've built into our controllers at the command level is the parallel gradient search. A gradient search is when you take two devices and you perform a small circular motion of one device with the other. And that causes a modulation of the figure of merit, optical power, whatever it might be. Small modulation of, of the signal as that dither proceeds. And then the controller observes that modulation in real time and drives it to the peak. So, and then it can do lock-on. You can track as well. And what's unique about this is that we can do this across multiple alignments, multiple alignment processes, inputs and outputs to silicon photonic devices, multiple degrees of freedom, multiple channels, all in one step. So that's why it's fast. And by the way, that was a slow motion view. Again, the actual time it takes to do the lock on is typically on the order of 300, 400 milliseconds. Very fast. So I've already alluded to some of this, but basically you can see here on the screen that the small circular motion causes that modulation in your figure of merit, such as optical power. You can see that at the left-hand edge of the circular dither, we have a maximum. At the right-hand edge, we have a minimum. And from that amplitude of that modulation and the phase of that modulation, we can determine which way is up. Where's the gradient? Where does it point? And follow that gradient to the top. And then from there, we can track it. If there's a drift process, such as a thermal process from turning lasers on or something of the sort, we can track that in real time. Gluing stresses, many different possible contributions. We can perform this tracking in real time. Again, across multiple channels, multiple inputs, multiple outputs, multiple degrees of freedom, all in parallel. It's very unique and enabling capability. Now, as I mentioned, optical power is typically the figure of merit for most silicon photonic devices, but there could be other things as well. For example, we have customers using this technology to square up the optics in their laser cavities. Today's lasers are very complicated devices with multiple elements that need to be aligned just so. And the position of each element depends on the position of the other elements. So those dependencies are what our parallel technique can unravel in real time to eliminate the time-consuming loops that would otherwise be required. Cameras, as you will see a few slides further on, the camera market is exploding, driven by smartphones, but increasingly automotive applications as well, autonomous vehicles and self-driving cars and things of that sort. So there, the quantity that you want to maximize when you're building the cameras is this thing called image quality. It's a calculation based on the image as presented at the image sensor. Maybe something like a Fourier transform or the modulation transfer function. There are plenty of proprietary approaches out there as well. Doesn't matter. Give us a figure of merit that rises to a peak and then falls. We will find that peak. So parallelism, I'm very fond of this slide because it shows sort of the way things used to be with single process alignments that took time. And then if you wanted to do more than one, you would have to do them one at a time. Versus this new advancement that not only are the alignments really fast, but we can do multiple alignments simultaneously and get the job done. So here's an example. This is a multi-core fiber called a Profo from a brilliant company on the East Coast of the United States called Chiral Photonics. They're looking, here you see basically a fiber, multi-core fiber. They call a pitch-reduced optical fiber array, Profo. And it is coupling with a chip. In this case, the chip was made by IMEC. You can see how many diffractive couplers there are there. They can make, I believe, up to 92 of these very precisely located diffractive couplers in the corresponding fiber cores. So we showed this being aligned in that lower right-hand picture there in one of our trade show demonstrations. Now, the traditional way of doing this is to make an XY alignment, pick one of the channels, line it up transversely, now make some small angular motions, but geometry being what it is, every time you make an angular motion, you de-align in X and Y. So you have to stop, realign in X and Y, and just perform that loop over and over again. Takes time. Now, the alternative now is do it all in one step. So we showed this about 5 years ago at Photonics West. We showed it for the first time using glass fiber arrays. Everybody understands them. Everybody understands how painful it is to get them lined up. So we put together this demonstration. You see, wrote a little software that will quickly do a There, that's the area scan. We've localized the main mode. We've locked onto it. That little circular motion, that's the dither, and we're done. It takes longer to do that alignment, which is both X, Y, and theta Z. It takes longer to describe it than to actually do it. And then we had customers tell us the next year, well, my device has inputs and outputs. Show us how to do that. So we did the same thing again with the optical fiber arrays. So again, we do the XY transverse alignment to identify the main modes. We lock onto it. We perform the theta Z, and we're done. The interesting thing about this video is there's twice as many alignments being performed as in the first video, but it takes about the same amount of time, and that's because it's being done in parallel. So you can see the benefit here. Now, what we've done is we've taken this parallel alignment technology, we've spread it through our product line. So we have our hexapod micro robots with their capability for performing 6-degree of freedom motions, and that means 6-degree of freedom automated alignments. With our piezo systems, we have any number of PI stages in different formats and form factors that allow the customer to build a solution to meet their needs. And now most recently, we've taken this technology. Uh, we purchased a company about 7 years ago, ACS, a leader in industrial motion control. I was actually an ACS customer before joining PI, so I was delighted when we joined up with ACS. And this alignment technology is now coming to the ACS controls as well. So you can have these arbitrarily complicated, arbitrarily large assemblies of very, very fast industrial quality stages, performing inspection, testing, assembly of photonic devices. Fast. Okay, so that allows us to put together some pretty imaginative demonstrations. Maybe you've seen some of these in recent trade shows. So for example, in the lower left-hand corner, we have some large stages scanning a substrate, like might be a printed circuit board, or it could be a carrier or a tray, and we're trying to find the needle in the haystack in that. This is something that customers need to do. And so scan the whole area very quickly using an area scan. Again, a single command, and that allows us to find and localize, lock in onto a particular emitter of interest. In the right-hand corner, we've combined some very, very fast direct drive rotational stages, showing how you can easily construct, you or a toolmaker can easily construct a assembly with multiple process workstations working in parallel. Here's another approach in that video. You can see using a large format gantry, you can do the same thing where you can combine multiple motion devices. In this case, you can see the hexapods, the nanocubes, the big gantry stages. So these are examples of how this architecture allows our customers and their customers to benefit from flexibility and speed that they can't get anywhere else. And speed, of course, time is money. And so it's very important if we're going to keep up with the scaling phenomenon that I described earlier, that 3 order of magnitude ramp that this industry is confronted with today, needs solutions like this. Okay, so currently there are 2 paths, 2 ways of doing things. First, just like in the early semicon days, you can build your own machines, or you can hire systems integrators to do the building for you. We have some good recommendations. Um, it's a very valid path, but the ecosystem is rising also. We're starting to see leading tool makers like FormFactor, MPI, Tegema, which is now part of Ediplan, spanning the spectrum of what people need to do. And that way we're getting to the point where the semiconductor industry is today, and it has been for some time, where you can build the necessary capacity just by issuing purchase orders. For the moment, both of these paths are perfectly valid, and we support them both. Now, one of our approaches has always been to work with the earliest entrants. This goes back 52 years, our history as enabling innovation in the semiconductor industry and others. And consequently, here 2 examples right here. FormFactor has been offering their fast photonic wafer probers now for what, 6 years, something like that. They were the first on the market, and they've just done an amazing job, and that helped drive that company. to be on Fortune 100's fastest growing company list. Another example is Tegema, which recently was purchased by Editplan, a very, very substantial manufacturer of uh, pick and place assembly equipment with global reach. So they took this technology and they leveraged the parallelism we've been talking about, and that made them 10 times faster than their nearest competitor for assembling photonic devices. So again, it's the sort of thing I think the industry needs. There's other types of innovation happening now as well. It's really great to see. Here's an example. One of the unicorns of the photonic industry has been this passive alignment where you could just assemble parts, and either through optical trickery, advanced optical design, or maybe some mechanical uh, tricks and mechanical advancements to have things snap together in a way. Well, Terramount's ahead of the pack in that regards with some very clear, very clever approaches to minimizing the optical sensitivity of parts to misalignment. Now, sometimes people say, well, why are you talking about this? Doesn't that reduce the need for automated alignment? And no, not really, because the industry is growing so rapidly. And quite frankly, what's best for the customers, what's best for us and everybody else as well. And for some applications, some configurations, this is a very promising way to go. So it's an example of this innovation that the industry needs. And increasingly, we are seeing photonic solutions going everywhere, all sorts of applications. So I mentioned cameras earlier. Now, I my car is a nice enough car, but it's by no means a super fancy car. It has 6 cameras in it. And recently I rented a Tesla. That thing must have had a couple dozen cameras in it of extraordinary quality, really high resolution stuff. So it could do image recognition and determine where threats were coming from 360 degrees around the car. It's amazing stuff. And it's an example of how the number of cameras is only going to increase. They'll be watching you, the driver, as well, to be sure that you're paying attention, not falling asleep. So this means more cameras and better cameras. Same thing that we've seen drive the smartphone industry over the past few years. So pretty soon our cars are going to look something like this. Of course, this slide is a joke. First time I showed it, somebody laughed and said, that must be in California. And I said, yeah, of course it's California. But it's also, there's a point to be made here that your cars you'll be purchasing over the next few years will have lots of cameras in it, and they need to be aligned. They need to be manufactured. Now, one thing that is not mentioned enough as a solution for customers, for companies who want to build and sell and scale photonic devices is the contract manufacturer market. There are some very big names out there involved in photonics, and there's some companies that are carving out niches for themselves and making significant investments in photonic alignment capability for building these devices. Like you can see on the screen here, I've selected Integric Technologies in Silicon Valley. They have a quick response capability for developing process assembly processes. Benchmark Electronics has a fabulous facility in the Phoenix area, Phoenix, Arizona. There's a lot going on in Phoenix, and they have a magnificent facility that is capable of doing the assembly work for these very precise photonic devices. Now, what about that last bullet point I mentioned? Collaboration, cooperation, partnering. Well, especially in Europe, there is an answer for that. That about I think it was 2013, the Economic Union, the European Economic Community, got together and said, how can we grow a domestic photonics market to serve the global needs for photonics? And so they came up with the Photonics 21 initiative, and that has involved a multitude of pilot lines, consortia, and public-private partnerships to provide access, expertise, and a path to volume production for these devices. I have a few examples here. One I personally involved in is Podium. Podium is based in the Netherlands, and it is uh, funded um, by the, um, the Netherlands government, and it is a group of now 5 participants that that each provides a certain amount of expertise. The notion here is to provide a critical mass of expertise so that when a customer, a global customer of some sort with a new photonic device and they need to get it into production, they can come to Podium as an example of one of these public-private partnerships and know that they are talking with some of the best minds in the industry to find best practices and the best path forward to scale rapidly, to get to market, and then keep pace with the needs of the market. So that's one example, very exciting one. As I said earlier, automation, innovation, cooperation. Let me give you an example. This is what I just learned about 10 days ago at the Laser World of Photonics in Munich. Visited a booth. Frankly, it was the Epic booth, and in it was a group of very bright people from Philips with who've been working with MedFab. MedFab is another of these public-private partnerships, these consortia dedicated to, in this case, medical diagnostics, a pilot line to allow companies that have developed technologies for the target area of interest and develop a path forward for manufacturing these things, fast tracking from concept to actual product in production. Now, this was a group from Philips that I was looking at that has worked within the umbrella of MedFab to bring to market smart catheters. Now, isn't that an interesting concept? This is a catheter, and here you can see one of the photographs here. That is one of these high data rate sensors on a matchstick head. So you get an idea of how small this device is. So what this involves is MEMS, mechanisms for managing the optical links, shrinking the optical interconnects to allow all this to be placed inside of a living patient, and assembly techniques to make all this happen. And there's a very interesting article about this. I put the QR code for it there. They demonstrated 25.8 gigabit per second in this device. That's pretty good speed. That's data center speed. And you need it for some of the advanced metrology and telemetry that will be benefiting our health as we go on. And they're looking at more and more examples of this, both invasive and uh, wearable technologies based on photonics. And this is all meant for both in vivo and in vitro applications. And it's being enabled by the MedFab Consortium, that public-private partnership that is in the business of helping companies take concepts like this into volume production by bringing together the necessary elements and then scaling, introducing these applications to the companies that can help make them scale rapidly. So this is all something that I just tripped over at the Laser World of Photonics and had this thrilling conversation with Philips. It just struck me as being an example, a really good one of everything that I've been talking about here, those 3 points: automation, innovation, and cooperation. Okay, so what about quantum computing? This wonderful graphic was produced by a consulting firm, and it you see the link for it there. It does a wonderful job of describing the multiple players and the multiple fields, multiple types of qubits. There's basically these 8 basic categories, and there may be more coming. It's a very, very fertile field, lots going on. But let's take a look at these and look at the photonic component of each of them. You might think that for a superconducting qubit, you might not need much in the way of photonics, and you would be wrong. Getting information in and out of that cavity needs to be adiabatic. You don't want to use wires as much as you can. They might go superconducting when you don't want them to, and they might produce heat. So photonics is a very important part of even this cryogenic type of superconducting uh, qubit. Um, trapped ions. Trapped ion qubits are profoundly photonic. They look very much like the optical tweezers that some of us have been working with in the biophysical world for a couple of decades here. In fact, Stephen Chu's work, for example, won a Nobel Prize for trapping optically tiny uh, spheres and atoms and things like that, so that they can be manipulated and used as tools for observing the molecular scale processes that are this thing we call life. Well, that same basic idea is being used to manipulate ions, to entangle them, and to position them for processing, for readout, and for calculation. So again, profoundly photonic, and another example of how photonics is super important to the quantum computing world. There is a class of quantum computers, qubits, based on photons. And there's some players such as PsiQuantum, when they came out of stealth mode about 2 years ago. Beautiful picture. I posted it on LinkedIn. That's a form factor wafer prober. And what's interesting about that is that you tend to be probing wafers when you're pretty far along in your engineering process. So anyway, that prompted an article that I wrote. Oops, sorry about that. Went one too many. Here we go. There we go. That prompted an article. There's a QR code for it in Physics World about how automated alignment is going to be really important for quantum computing as well. And of course, the quantum world is about much more than just computing now. Quantum sensors are a big deal, quantum communications, quantum key exchange. We're just getting started. And it's a really, really interesting field, and it will involve photonics. Most qubits will require photonic elements, which means that the same dynamics I've been talking about earlier for cameras and for interconnects, that same need to scale is there for the quantum world as well, as it makes the transition to industrialization and commercialization. So basically, I'm nearing the end of my slides here. The deluge approaches. That's good news, but it's sobering news as well, because we as an industry have to figure out how to keep pace with this step function that we're being asked to track, that 3 order of magnitude step function. Many, many, many new applications, they're all adding into this issue, this problem. Um, Consumer applications are now in the game. Things like autonomous vehicles, things like optical cables, things like wearable technologies. That's a big difference from just a couple of years ago when photonics was all about the data center. There's serious challenging to scale. I've given you several times the 3 elements that are necessary: automation, innovation, and cooperation. So, of course, all these technologies need to keep pace. The yields must improve. These are all things that we together need to work on. And you'll see this thing called silicon photonics, which may be based on other substrates. I'm using the term as sort of a catch-all. It is the key, not just to the future of certain technologies, but so many technologies all over globally. PI, of course, we're here to help. It's our heritage, is to help these industries as they are being born, to enable them. It happened in the semiconductor industry. We grew up with the semiconductor industry starting 52 years ago. And today you cannot make an advanced chip without PI someplace in the value chain, in the lithography column, in the wire bonders, in the inspections, and PIs everywhere. And that's because we grew up with that industry. Genomics automation. If you're so unfortunate as to need a genomic scan made of a tumor or a pathogen or something like that, chances are very good a tool will be employed that includes PI at its heart because we enabled that industry from its infancy. And so it goes with silicon photonics as well. And that's the challenge for all of us. So my last slide. Basically, please keep in touch. This notion of parallel alignment automation very often has people wondering, well, how can that work? How can that possibly work? Well, we have a tech note. Feel free to ask your local PI sales or applications engineer for a copy of that. Be happy to send it to you. My own contact information is there both on WeChat and LinkedIn. Please feel free to reach out. And now I guess it's time for our questions.
Thank you very much. Yeah, we do have time for a few questions. Everyone, if you have not already, please enter those into the chat and we'll get to as many as we have time for. So my first question for you is, my company has a component design, but we are unclear on the best path for ramping. What do you recommend for first steps?
Well, I would say I would first, if it were me, I would reach out to those consortia that I mentioned, the ones that are in Europe. We have AIM Photonics initiative here in the United States. Uh, these are global resources, and they represent an access path to talking to some of the most experienced people in the field. So I would say that would be the first place to start. If for example, you would like an introduction to some of these people, feel free to send me an email or a message, and I'll try to give you an introduction to the correct people to make this happen quickly for you.
Thank you. So the next question is, how credible is the 3 order of magnitude step function in demand that you mentioned? Photonics had a big crash 20 years ago. Should we be concerned that could happen again?
Never say never, but I would say no, I'm not concerned. The reason is that back in 20 years ago, I think I mentioned this really early in my presentation. The field was driven by one application that was replacing satellite telecommunications links for long distance phone calls, replacing that with transoceanic, transcontinental fiber links. That was it. That was photonics right there. That and things like pigtailing the lasers to enable those interconnects. Basically one application, and they laid enough dark fiber. If you're going to lay a transoceanic cable, you might as well add some extra fibers so that you have enough cable to get you through the next few years, and that's exactly what they did. So around 2002, I remember the OFC conference was dead. Where were all the customers? Well, for now, the market had dried up. I don't think that's going to happen again. Too many applications. We've mentioned how many of them so far: social media, streaming networks, global webinars, um, selfies, the, the tens of petabytes of data that are uploaded to the cloud every year just from people taking pictures of themselves. It's something nobody saw coming. And that data needs to be conveyed from place to place, needs to be routed, needs to be stored, needs to be filtered and shared. And so that's just one example. And now we're adding autonomous vehicles, we're adding, quantum computers, optical computers, so many applications. So no, I don't think that's going to recur. I really don't.
All right, perfect. Thank you. The next question is, the semiconductor industry adopted standards quickly. Do you see that happening in photonics?
Maybe. There are attempts, but I tell you, I see some of the package designs, and it's clear that the standards aren't happening fast enough. So that's fine. That just means that we have to be flexible and we have to adapt. And that any solution that companies like PI comes up with needs to be able to be mapped to different types of packages, devices. It needs to be flexible. So yeah, standards. I've sat in on many standards meetings and so forth. I don't see it actually gaining the necessary traction quite yet, but it's not like the semiconductor industry where they standardized on first 4-inch wafers, then 6-inch wafers, and then 8-inch wafers. And you will notice that most of the industry skipped over the 6-inch wafer. And that wasn't because of any standards issue. That was because the 800-pound gorilla of the semiconductor industry back in the 1990s was IBM. They went directly to 8-inch wafers. And so consequently, they had a market power that was a de facto standardization tool. Because IBM wanted 8-inch wafers, the whole industry ended up supporting 8-inch wafers. Nobody in the photonics industry has that kind of market clout today. So flexibility is the key word.
All right, perfect. Thank you. The next one is, what about system integrators? Are they a solution for building equipment optimized for my devices and processes?
Yes, definitely. We know some good ones. The the key to systems integrators is they tend to be sort of local, tend to be, and the applications tend to be global. So you need to be sure when you're talking with the systems integrator that they have the necessary people with the fab class support capabilities where they are needed in the world. So one in particular that I've been working with recently, it's a very impressive group, is GES, that is part of Kimball Electronics. It's a substantial company. They have some really, really impressive people who know photonic alignment. So yeah, the systems integrators chosen correctly could be a real asset. I would just caution against going down the street to, Joe and Ed's systems integration company. Because they probably won't be able to support you globally. That's a very important consideration that I think should be part of the initial selection criterion for a systems integration partner. Again, if you have any questions or you'd like to kick this around, send me an email. I can provide you with some suggestions and introductions to try to save you time.
Okay, perfect. I think we have time for one final question. It is, what about passive alignment components that snap together like Legos? You mentioned Terramount, but are there other solutions?
There are lots of solutions coming out there. This has been the industry's unicorn for 35 years. People have been looking for that way of just bolting things together like Legos. But again, at its root, the alignments need to be really precise, need to be accurate down to the tens of nanometers levels. Unless you perform some optical trickery, some mode expansion, things of that sort, to make the tolerances more tolerant. Um, there are some approaches. They tend to be sort of application specific in the sense that I don't see a single solution that's going to solve everybody's problems. I do see some solutions out there that look very promising for reducing the pain of some specific types of interconnects and some specific types of alignments and assemblies. Um, a Terramount was a really good example of that. This optical plug capability that they put together that is reduces the uh, sensitivity of the misalignments. It's very, very clever. And yeah, there are more out there. There are people, IBM's been working on techniques for some very precisely fabricated, lithographically fabricated V grooves and things of that sort. So there will be a continuing innovation and continuing uh, evolution in that field. But I don't see active alignment going away anytime soon. I see it being a need. How are you going to use passive alignment at the wafer level for probing wafers to make sure that the chips are worth packaging in the first place? I don't see that being a generic solution except using active alignment. So yeah, there's room enough in this industry and the growth that we're looking at for a multitude of applications, a multitude of approaches to be implemented. So yes, you will see more in the field of passive alignment. You'll see PI being involved in many of those applications because even if active alignment isn't necessary, precision positioning is. So it's a very interesting field, and I think you will see many, many more innovations coming.
All right, thank you. And everyone, if we have not already answered your questions, please look out for a reply from us later by email. If you have another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That is webinar@photonics.com. And just a final note, this whole session was recorded and it will be available on Photonics Media website shortly. You will also receive an email for that. And I'd like to thank our presenter one last time, Scott Jordan of PI, and all of you for participating in today's webinar. It was presented by PI and hosted by us at Photonics Media. Thank you.
Thank you, everybody. Bye-bye.